Hey guys, hopefully you can hear and see what I'm seeing, but today we're going to go over hash tables. Specifically, many applications require a dynamic set that supports only the dictionary operations, insert, search, and delete. For example, the compiler that translates a programming language maintains a simple table. Okay. The keys of elements and a hash table is an effective data structure for implementing dictionaries. That's what it does. Although searching for an element in a hash table can take as long as searching for an element in a linked list, sometimes O(n). In practice, hashing performs extremely well, and under reasonable assumptions, the average time to search for an element hash table is O of 1. Hash table generalizes simpler notion of an ordinary array. Okay. Directly addressing into an ordinary array makes effective use of our ability to examine arbitrary positions in an array in O1 time. Does that make sense? So basically saying hash table basically takes whatever an array does and generalizes it. So it takes some of the things, just makes it bigger for everything. And we can find any cell of an array in O1 time using the index, which makes a lot of sense. And the number of keys actually stored in it, when the number of keys actually stored in it is relatively small to the total number of possible keys, hash tables become an effective alternative to directly addressing an array. Okay, so if we have only n and n squared are the total number of keys, then it's probably pretty good. So the hash table typically uses an array size proportional to the number of keys actually used. Maybe this is not, but maybe 1 to 4 n or 1 to 5 n, for example. The array index is computed from the key. Section 11.2 presents main ideas focusing on chains and collisions, yada yada yada, how we compute, and this is basically like what it's going to tell us. We don't really need that. Let's start with direct address tables. Direct addressing is a simple technique that works well when the universe U of keys is relatively small. Suppose an application needs a dynamic set in which each element has a key drawn from the universe U. So we have a dynamic set which changes, and each time it needs a new key, it's pulling from this until m-1, where m is not too large. Okay, again, m is not like 1 trillion or something. Maybe it might be 100,000, maybe 1 million, depending on how it is. Maybe smaller than that even. To represent dynamic set, we use an array or direct address table denoted by T0 to m-1, in which each position or slot corresponds to a key in the universe U. Figure 11.1 illustrates the approach. Slot K points to an element in the set with key K. If a set contains no elements with key K, then TK equals no. Whatever that means. Oops, that's things I don't get in this thing yet, but I'm still learning, so it's okay. So direct search table uses the table T and key K and returns T of K. Again, same way an array does. So you insert a new element simply by using the index x dot key, and we're saying the key of x is equal to x. If that makes sense. Direct address delete, we just set the x key equal to no. Let me just take a second. Okay. Each of these operations only take one time. Each of these operations only take one time. Makes sense because they're just adding new stuff. Okay, how could we implement a dynamic set? By direct address table T. Each key in the universe U corresponds to index in the table. Then the set K of actual keys determines the slots of the table that contains pointers to the elements. So saying these are the whole table, data table, how much we have storage, and then we have these keys that define to them. Okay, that makes sense. This is easy. You can do these by yourself. Okay, I would leave this to you for a challenge problem. I'll do it myself later, and we can go over it next video. Let's go through hash tables now. So just review, that was direct address tables. These are hash tables, and they're probably more important. The downside of direct address is obvious. If the universe is large, storing the table is impractical because you have to save all that memory, or even impossible given the memory, right? Because you have to have that continuous memory for all those indexes, and half of them won't even be used. It's hella fast though. Furthermore, the set K of keys actually stored may be small, so small relative to U that most space allocated for T would be wasted. The set K of keys stored in dictionary is much smaller than the universe U of all possible keys. When it's very small, then a hash table is better because it's much less storage than a direct address table. Specifically, we can reduce the storage requirements to O of K, while we maintain the benefit that searching for an element in a hash table still requires only O of one time. Okay, so that means this is not O of K, this is theta of K, so we only need theta of K storage, and we still keep our O of one time. This catches the bound is for the average case time, whereas for direct addressing, it holds at the worst case time. Direct addressing, an element with key K is stored in slot K. With hashing, the element is stored in slot HK. What that means is, in this earlier table that we're doing, it was simply done in K. When we do a hash table, it's putting it into a function H, then outputting that sort of slot or index, which is a little bit more complex, but we use a hash function to compute the slot so that we can also get it back. It's a little bit better, whereas the size Or for hash functions, I believe you don't always want to get at that, but we'll look into that later. Let's see what it says. Whereas the size m of the hash table is typically much less than the size of u. Duh, right? Because when we try to get to m, we're trying to have a smaller subset. We say that an element with key k hashes, 2-slot h of k. We also say that h of k is the hash value of key k. Does that make sense? K hashes, 2-slot kx. So if it has k hashes, we're basically mapping it because we're using that sort of function. We also say that h of k is the hash value of k, just because that's what we get from the function. Figure 11.2 shows the same idea, and how we're simply looking at these four values, even though this is simply k of 1. Why are we not putting it here? This is what the hash value gives us, k of 4. We're putting it here. K of 2 equals k of 5. For some reason, I don't understand, but good job. Using the hash function, 2 hash table slots. Because K2 and K5 map to the same slot, they collide. Collision is bad. They do stuff. And these are actual more collisions, and this is how you actually fix it. You then use this sort of linked list approach. Like before, that allows you to go through each element that is colliding into this using 2 main data structures. We are creating this hash table. We're using this direct address table, and we're using linked lists. So just an easy way to remember. Sorry, I forgot the page we were on. 2 things: direct address table and linked list. There's one hitch. 2 keys may hash the same slot. We call this a collision. We have an effective technique, again, by just linking them all together. We try to achieve this goal by using suitable hash function h, which is the ideal solution, but sometimes it does happen because h is random. The very term hash means invoking images of random mixing and chopping to this approach. Deterministic that the given input is k should always produce the same output, h of k. However, there must be at least 2 keys that have the same hash value, avoiding have the same hash value. Avoiding collisions altogether is therefore impossible. Thus, well-designed random-looking hash function can minimize the number of collisions. We need a method for resolving collisions that do occur. The remainder of this section presents a simple collision resolution technique called chaining, which introduced alternate method called open addressing. So there's 2 different ways of doing this. Alternative, which we'll go over later, and chaining right now, which we'll go through, and then open addressing, which we'll go on later. I wonder how this works. Oh, it's very interesting. I wonder if we write this, does it stay? Oh, okay. We'll go like this then. So in chaining, I guess we can't erase in here. In chaining, we place all elements that hash the same slot in the think list. So that J contains a pointer. I don't like this, Loki. Sorry, guys. In chaining, we place all elements that hash in the same slot in the same linked list, as shown earlier. And then figure 11.3 shows that same sort of thing, the linked list. You can see that again, how it has those arrows pointing in those directions. Then like that. It's pretty chill. And it's doubly linked. We have slot J contains a pointer that points to the head of the list of all stored elements of hash J. There are no such elements. Slot J contains no. Okay, the dictionary operations on a hash table T are easy to implement when collisions are resolved by chaining. Right? Makes sense. You basically just search through a linked list. Like if it's this element, go here. If not, then keep on going and don't select that one, right? But then if it's this one, you go here, check it, no, but then go to the next one, and like that. Simple linked list. And how we actually implement these things is, this is how we insert a chained hash. Insert X at head of T, X of this. So we always insert at head IC. Chained hash secret. Search for element with key K in list of this. And then it keeps on going until it finds it, and then delete it from the list. Right, because it's literally the same thing. We're just looking for that key. Once we find that key, then we delete it. The worst case running for insertion is O of 1, again because it looks for the first element, so it's really good. Insertion procedure is fast. For finding it, you can find it O of N. I would also say that deletion is also O of N. I guess if it's doubly linked, that actually changes the time a little bit. We'll look at that later. Okay. We assume the element is being inserted is not already present in the table. If necessary, we check this assumption on additional cost for an element whose K is before we. At searching, the worst K is proportional to the length of the list. We shall analyze operation more closely. We can delete an element of 1 time. And that makes sense because as soon as we see the element, we see it. I believe that, interesting. So since it takes element X into input and not K, it's a little bit different and is. I'm gonna go find a solution for this later when we take a break in 1 minute or so, but yeah. So we don't have to search for X first. If hash supports deletion, then linked list should be doubly linked. So we can delete an item quickly. If the lists were only singly linked, then to delete item X, we'd first have to find X in the list of this so that we can update the next attribute, X predecessor. With singly linked lists, both deletion and searching are the same asymptotic running times. And I'm going to stop there for right now. We're going to come back and watch